See this example 4.8, that is also the application of Ampere's circuital law. Figure shows a long straight wire of a circular cross section carrying steady current I. The current I is uniformly distributed across this cross section. Calculate the magnetic field in the region R less than A and R greater than A. Now see here, we can solve this example using Ampere circuital law. Now see, this one is the current carrying conductor having radius equal to A. It is carrying current I. Here we consider this thing, this total current I flowing through this conductor is uniformly distributed over its cross-sectional area. Now we want to find the magnetic field at a point outside this conductor as well as at a point inside the conductor. Now see, suppose first we consider the point outside the conductor, which one is at a distance r from the axis of the conductor, where r is greater than a. Okay. Now, for r is greater than a, write down the Ampere circuital law, integration B dot dl equal to mu 0 sigma I. Now, consider the Amperian loop having radius equal to r. Now, on the circumference of the loop, at any point, magnetic field B and the line element dl will be tangential one. So B and dl will be parallel. So theta, that is 0 cos 0 1. So here on left hand side, integration B dl cos theta, that is equal to mu 0 sigma I, that we can write B integration dl cos theta is 1 mu 0 sigma I. Now B integration dl, that is the circumference of loop, 2 pi r mu 0. Now sigma I, that is the net current flowing through the Amperian loop. Now see, Amperian loop is enclosing entire current because your entire conductor is inside the loop. So total current flowing through the loop itself is I. So sigma I, that you can write I. So B, that is equal to mu 0 I upon 2 pi r. And here we can observe this thing, B proportional to 1 upon r. The same equation previously we derived for the infinitely long wire. Now we have to find the magnetic field at any point inside the conductor. Now see here, we consider a point inside the conductor at perpendicular distance r dash from the axis of the conductor. So here we can consider the Amperian loop with radius equal to r dash as shown in this figure. Now, magnetic field at a point inside the conductor means r less than a. Again, we can write the Ampere circuital law for that. That is integration B dot dl mu 0 sigma I. Now, integration B dl cos theta, theta is 0. So, cos 0 1. That is equal to mu 0 sigma I. B is same everywhere. So on the circumference of the Amperian loop. So it is taken outside the integration. B integration dl, that is equal to mu 0 sigma I. Now here important thing, that is to find out sigma I. Sigma I, that is the net current passing through the Amperian loop. Now see, total current I, that is uniformly distributed over the entire cross section of the conductor. Area, cross sectional area of the conductor, that is pi a square. So total current I is uniformly distributed over the cross sectional area pi a square. So we can use simple unitary method. On area pi a square, current I is uniformly distributed. Therefore, current through unit area is how much? So simply we can write current through unit area, that is I upon pi a square. Now, through unit area, if the current is I upon pi a square, then through the area of the Amperian loop, how much current is flowing? So multiply it by area of the Amperian loop. So we can say sigma I, the total current passing through the Amperian loop. That is, current passing through unit area, that is I upon pi a square, into area of the Amperian loop, that is pi r dash square. Pi cancelled. So I upon a square r dash square. So here we can write now B integration dl, that is 2 pi r dash mu 0 as it is, and sigma I, which we calculated here, substitute I upon a square r dash square. So here 1 r dash cancelled. So B, that is equal to mu 0 I upon 2 pi a square into r dash. So here we can observe this thing, B proportional to r dash. So here if we draw the graph of magnetic field versus the position of the point from the axis of the conductor, then on the axis the magnetic field is 0. Then as we move away from the axis up to its surface, the magnetic field directly proportional to r. So straight line graph. Then outside it, magnetic field proportional to 1 upon r, means from the surface it decreases as we move away. So this is the graph of B versus R. Clear to all of you?